Hi everyone, welcome to CVPR 2021 tutorial, Normalization Techniques in Deep Learning, Methods, Analysis, and Applications. This is Lei Huang. I'm an associate professor from Beihang University of China. As everyone knows, deep neural networks have been extensively used across a broad range of applications, including computer vision, natural language process, speech and audio process, and so on. Deep neural networks are typically composed of stacked layers. The transformation between layers consists of a linear mapping with nullable parameters and a nonlinear activation function. While their deep and complex structure provides them powerful representation capacity and a major advantage in learning feature hierarchies, it also makes their training difficult. For example, a graded explosion or vanishing problem. In fact, the success of deep neural networks heavily depends on breakthroughs in training techniques, which has been witnessed by the history of deep learning. For example, normalizing initialization techniques pioneered the way to design varying initialization methods on linear layers for providing well-shaped gradients. This makes training deep models possible. Its current Google Scholar citation is over 50,000. The famous random activation solves the gradient situation problem of previous sigmoid nonlinearity and improves the training performance. One method techniques in addressing the training issues of deep neural networks was batch normalization. It standardizes the activations of intermediate deep neural network layers within a mini batch of data. Batch normalization improves deep neural networks training stability, optimization efficiency, and generalization ability. The Google citation of batch normalization is currently over 28,000. Batch normalization is a basic component in most state-of-the-art architectures and has widely used throughout various areas of deep learning. For example, batch normalization is a key measure of residual network and denseness for stabilizing the training. Further, a significant number of other normalization techniques have been proposed to address the training issues in particular contexts, further involving the deep neural network architectures and their applications. For instance, linear normalization is an essential module in transformer, which has advanced the state-of-the-art architectures for natural language process tasks. Importantly, the ability of most normalization techniques to stabilize and accelerate training has helped to simplify the process of designing network architectures. Training is no longer the main concept, enabling more focus on developing components that can effectively encode the prior knowledge into the architectures. Here is the statistics of publications on May conferences between 2020 to 2021. For example, ICNIR, CVPR, Simulurps, and so on. We found there are over 77 papers relating to normalization. Note that the number shown here is based only on the title of the paper. I believe there are more papers relating to normalization. These papers involve theoretical analyses of normalization techniques, design new normalization methods, or tailoring normalization techniques for different applications. The title of this paper is often looks like this, for example, certain normalization of whitening, or we think batch normalization in certain tasks, or towards understanding certain normalization in certain perspective, and so on. We can see normalization techniques is an active research topic because they are widely used in variant network architectures and heavily affects the performance of different tasks. Okay, this tutorial will address the following questions. Why there are so many normalization variants showing up in deep neural networks? What are the main motivations behind them, and how can we present a taxonomy for understanding the similarities and the differences between a wide variety of approaches? How can we reduce the gap between the empirical success of normalization techniques and our theoretical understanding of them? What recent advances have been made in designing alternative normalization techniques for different tasks, and what are the main insights behind them? Okay, our tutorial includes four parts. In the first part, we provide a unified picture of the main motivations behind different normalization methods from the perspective of optimization. In the second part, we provide a comprehensive review of the normalization methods, including normalized activations, normalized weights, and normalized gradients. In the third part, we discuss the recent progress in our theoretical understanding of batch normalization and provides clear guidelines for understanding why batch normalization stabilizes and accelerates training and further improves generalization. In the first part, we provide a review of the application of normalization for particular tasks and illustrate how normalization methods can be used to solve the key issues. We show that normalization methods can be used to edit the statistical properties of layer activations. These statistical properties, when designed well, can represent the style information for a particular image or the domain-specific information for distribution of a set of images. Okay, I will also provide some disclaimers. This is a huge topic with a vast multidisciplinary history. We will inevitably miss important related work, and it is impossible to provide a comprehensive list for all the related work. One can check this GitHub link to see a more comprehensive list of the papers. Each citation here is only meant as representative examples. One can search the related topics based on these representative examples. There are no consistent understanding of normalization, and there are different views in understanding normalization techniques. This tutorial is one. And the main source of this tutorial is based on our survey paper, Normalization Techniques in Training Deep Neural Networks. But with the recent new updates, email me with pointers or suggestions, and I will update the slides or the GitHub. So I first introduced the task we care about and some notations. I talked about the supervised learning. Given the dataset, the input X, output Y, our purpose is to learn function or conditional distribution, which can model the mapping between the input and the output. Generally speaking, there are two types of models, that is, the non-parametric model and the parametric model. For the non-parametric model, we usually store the training set when doing prediction for the new input. The model predicts the output of the input X based on the similarity between the input and the stored training examples. It seems that there are no explicit learning process. For parametric model, training is just like transferring the input-output pairs into the parameters data. This tutorial focuses on parametric model, especially the deep neural networks. The training can be described as minimizing the loss, which describes the differences between the predicted one and the expected one, where head y is the target. For machine learning, it's not just the optimization task and memory the training data. We usually expect the model has generalization ability. That is, for the data outside the training set, the model also has good performance. Here, we show the definition of normalization from Wikipedia. There are different definitions from different areas. In statistics area, normalization is defined as the adjustments of values or distributions in statistics. In image process area, normalization is defined as changing the range of pixel intensity values. In data processor area, normalization is defined as the general reduction of data to canonical form. In this tutorial, we provide the definition of normalization as follows. We address that normalization is just a function transformation and ensures the transformed data has certain statistical properties. For example, if we use the standardization for normalization, we center the inputs to ensure the zero-centered data and scaling the data to ensure unit variance for each dimension. This definition is indeed more general than the traditional definition. The main reason of why we use this general definition is that there are so many papers using this definition implicitly. Besides, controlling the statistical distribution of input or activations in deep neural networks is what normalization could be expected. Normalizing the input data is a widely used data process. For example, it is advocated in many textbooks or courses that we need to normalize the input data. Why we perform normalization for the input data? There are two perspectives of normalization types. The first benefit is that it can improve the model's learning performance, especially for the non-parametric models. For example, the k-nearest neighbor classifier or color support vector machine, in which we need to calculate the distance or similarity between the examples. If some dimension dominates, for example, the range of third dimension is between 0 to 1, while another dimension is between 0 to 1000, then the distance or similarity will be dominated by the dimensions with large ranges. This will affect the performance of the learner. The second benefit of normalization is to improve the optimization efficiency for parametric models. For instance, the logistic regression methods. In this method, there is no closed solution. Therefore, the iteration-based method should be used. In general, gradient or stochastic gradients are used to update the weights. For these models, normalization can help having a better optimization landscape, which means that given randomly initial parameters, your optimizers are easier to arrive at the optimal points. To illustrate it, here is a simple linear regression with mean square error as a loss function. The left subfigure shows the input with different scale in zero dimension. In this case, the landscape will be like an oval with non-isometric shape. For this kind of landscape, it is more difficult to optimize and usually shows a zigzag trajectory with gradient updates. Owing to the gradient is perpendicular to the loss curvature. If normalizing input is used, as shown in the right subfigure, we can find that the landscape is more like a sphere. In this case, The optimization problem is either to get the optimal points with gradient-based methods. This is a high-level motivation of why normalizing the input helps from the view of optimization. Here, I will provide some reasons mathematically why normalizing inputs helps optimization. Let's consider the linear regression with mean square error loss. To rewrite the formulation, we can get these objects, where C is the covariance matrix. Generally speaking, the shape of optimization landscape for this simple linear model is controlled by the Hessian matrix. It can be easily derived to this formulation. We can find that the Hessian is the covariance matrix of the input. Therefore, the distribution of the input data controls the optimization landscape. The second-order methods, for example, Newton's methods, can be viewed as the gradient multiplying with the inverse of the Hessian. If x is normalized, especially written that is, it has a normal distribution, then the landscape is easier to optimize. There is more detailed conclusions showing that how the learning dynamics for optimization are controlled by the spectrum of the Hessian matrix. For instance, the maximum eigenvalue of the Hessian matrix controls the optimal learning rate for convergence, and it also controls the upper bound of the learning rate. That is, if learning rate eta larger than 2 over the largest eigenvalue of the Hessian, the training will diverge. Another important concept is the condition number, which is defined by the largest eigenvalue of Hessian over its smallest eigenvalue. The condition number controls the iteration required for convergence. For more details of the concrete theoretical results, one can check the Quinn's paper published in 1990. If a Hessian is an identity matrix that can be obtained by writing the input, the gradient descent can converge within only one iteration. Therefore, normalizing the input can surely accelerate convergence during the optimization of linear models. In the previous results, we only discussed the output with one neuron. It is easy to extend to the output with multiple neurons, where the Hessian is represented as this formulation. Its shape is also controlled by the covariance matrix of the input. So, let's further to discuss the normalization techniques in deep models. These theoretical results for linear model do not apply for deep neural network because deep neural network are nonlinear model, even though it includes layer-wise linear transformation. However, the input X is only linearly connected by W1, but the optimization is over all the parameters theta, not W1 only. Despite of the nonlinearity, we can exploit the layer-wise structure of the deep neural networks. We can find that HI is linearly connected by Wi plus 1. This means normalizing activations can benefit the optimization intuitively based on the theoretical results for linear models. Okay, let's give an illustration of this intuition under the framework of proximal backpropagation. Under the proximal backpropagation framework, the optimization can be further relaxed to optimize the weighted theta and the hidden activation Z jointly, which can be described as the regularization term here. If lambda equals infinity, This optimization process can be reduced to the standard backpropagation algorithms. Indeed, we can also use the backmatch propagation algorithm proposed in Zhang et al. To optimize the Z and W jointly. For a parameter as Wk in the k-snare, whose target signal is obtained by the updates of gradients from the upper layers described here. Therefore, all the optimization problems can be described as this group of sub-optimization problems. We can find that each sub-optimization problem can be viewed as linear model. Therefore, normalizing the activation normalizing as described in the previous theory for linear model can also benefit the optimization for deep neural networks. For more details to understanding these intuitions, please refer to these 3 papers. Another theoretical basis of normalizing the activations benefiting optimization is from the perspective of approximating the facial information matrix. The facial information matrix can be approximately used to describe the optimization landscapes. One successful example is approximating the facial information matrix of deep neural networks using the Kronecker product. In the Kronecker product approximation method, there are 2 assumptions. First, weight gradients in different layers are assumed to be uncorrelated. Second, the input and output gradient in each layer are approximately as independent. Therefore, the 4 facial information matrix can be represented as a block diagonal matrix, that is Fx diagonal F1 to Fl, where Fi is the sub-facial information matrix, that is the Fim with respect to the parameters in a certain layer, and computed as by this formulation. We can see that each sub-facial information matrix is controlled by its covariance matrix of layer input and the covariance matrix of output gradients. Therefore, the optimization landscape of the optimization problems can be approximately controlled by the covariance matrix of the input and the output gradient. For simplicity, we denote sigma x as the covariance matrix of the input and the sigma gradient h as the covariance matrix of the output gradient. Okay, based on the previous theory, we can see that if we ensure the following 2 criteria, the condition of the facial information matrix can be improved. The first criteria is that the statistics of the layer input and output gradient across different layers are equal. That is, the magnitude of different layers are equal. The second criteria requires sigma x and sigma gradient h while conditioned. The second criteria is similar to the conditions discussed in the previous theory for the linear model. Here, we will see that a variety of tactics for training deep neural networks have been designed to satisfy criteria 1 and or criteria 2 essentially. For example, the most famous rate initialization technique aims to satisfy criteria 1. Archival initialization method aims to obtain nearly equal variance for layer input or output gradients across different layers. Her editor extends this idea under the network with random nonlinearity. Orthogonal initializations are designed for satisfying the criteria 1 and criteria 2, where it aims to ensure the eigenvalues of the output Jacobi with respect to the input are nearly equal to 1. Even though these famous initialization methods provide very good conditions for optimization and make training very deep neural network possible, However, these good properties for optimization can be broken down and is not necessarily sustained throughout training due to the update of weight matrices. From this perspective, it is important to normalize the activations in order to produce better conditioned optimization landscapes, similar to the benefits of normalizing the input. Therefore, we can see the general goals of normalization in training deep neural networks are controlling the distribution of the activation or output gradients during training. This is the key motivation of normalization in training deep neural networks. One key question is, what kind of normalization we should use for benefiting the optimization? As analyzed before, better condition number of hash matrix or imported covariance matrix is easier to optimize. Therefore, we expect to normalize the activation such that it has better condition of the imported covariance matrix. There are three intuitions. For example, centering, scaling, and decorrelating can benefit this as shown in the previous paper. Centering operation makes sure the input has zero mean. Scaling ensures the distribution of each dimension has the same variance. Decorrelating decouples the input dimensions and ensure each dimension has independent contribution for the noise. Besides, we also can combine the barrel operations. For example, we can use standardization, which not only standardizes the input, but also scaling each dimension such that the variance for each dimension is zero mean. The most elegant normalization should be whitening, which is centering, decorrelating, and scaling the input and ensure the input has the homogeneous diagonal covariance matrix. It ensures the optimization landscape like a sphere, which is easier to optimize, as discussed before. In summary, from the perspective of optimization, normalization aims to provide a better optimization landscape by controlling the distribution of activation and output gradients. To take a multiple layer perspective, for example, given the input for each layer, we can calculate the pre-activation by linear transformation and then get the layer output activation with the nonlinearity function. By forward, we get the prediction of the final output. Given the designed output, we can calculate the noise, then we can get the gradient with respect to the activation. We also get the gradient with respect to the weight for each layer, which relies on the input and the output gradient in this layer. Therefore, we can explicitly normalize the pre-activation or the activation to obtain the designed distribution. Or we can normalize the weight with a constraint distribution to implicitly control the distribution of the activation and output gradient activation. We can also normalize the gradient. Normalizing gradients exploit the curvature information for gradient descent or stochastic gradient descent. Even though the optimization landscape is air-conditioned, this involves performing normalization solely on the gradients, which may effectively remove the negative effects of the air-conditioned landscape caused by the diversity of magnitude in gradients from different layers. That is, criteria 1 is not well satisfied.